In this video, we will discuss about some important sorting algorithms with n-square time complexity. There are better algorithms in terms of time complexity available, but learning these outdated algorithms will help us in building the foundation. There are three sorting algorithms that we are going to discuss. Most important thing is that you learn to code the logic. You need to develop the skill of converting your logic into the code. This is the skill that we are trying to develop by learning all these outdated algorithms. So what is sorting, by the way? Given an array that contains n element, your task is to sort the element in increasing order. That means arrange the elements in increasing order. So this is what we call as a sorting in increasing order. So this is the input array that you have 1, 5, 2, 10, 8, 13 and 3. This is random order, and the second array that you have is a sorted array, and sorting is done in ascending order. Once you understand what sorting is, let's directly deep dive. The very first sorting algorithm that we are going to see is a bubble sort. The key operation in this sort is swapping of adjacent element if they are in wrong order. So if let's say you have two different numbers 5 and 3 in given array, they are, let's say, arranged something like this. So 5 and 3 are in wrong order. So what we do, we swap them and put them into the correct order. This is the key operation that we are going to do here. So why exactly are we doing this particular operation? The operation is based on the observation that if we iterate the whole array and keep on swapping the numbers who are not in correct order, then the largest number will reach the end of the array. So by the first iteration, maximum number will go to the end. After k iterations, the largest k numbers will be at the last k positions. Let's look at the example for the better understanding. So you have this array 3, 10, 5 and 2. Initially, our iterator I is pointing to number 3. Then we check whether 3 and 10 are in correct order or not. They are in correct order, right? Because 3 is less than 10. So they are in correct order. So no worries. So our iterator I will now point to 10. Again we do the exact same operation. We check whether our element 10 and 5 are in correct order or not. Here they are not in correct order. So we need to swap them, right? That's what the algorithm tells us to do. So we are going to swap these two numbers. Here we will have 10 and here we will have 5. Once swapping is done, we will move our iterator I to the next position. Now our I is pointing to the updated number 10. This 10 and 2 are again, they are not in correct order. See, 10 is greater than 2. So again what we do, we swap these 10 and 2. So here we will have 2 and here we will have 10. So this is the result after the first iteration. 3, 5, 2 and 10. If you look at this carefully, this element 10 has reached the end of the array. Why? See, when you are iterating from left to right, what you check? You always check whether the elements are in correct order or not. Let's say there exists an element which is the largest element. Here in this case it was 10. If you put that 10 in any place other than the last place, this will create a wrong position and you will end up swapping that element with the next element. You get my point, right? You put largest element at any position other than the last position, you will create a wrong arrangement. So our algorithm will end up swapping that particular element with the next element. In this case, 10 was in a wrong position. 5 was less than 10. So we swapped. Again, 10 was in wrong position because 2 was smaller than 10. Again we swap. And that's how 10 reached the end after the first operation. Now let's look at this second iteration. Same thing, we check whether 3 and 5 are in correct order or not. So they are in correct order. So we update the iterator. Now our I is pointing to 5. So we check 5 and 2 are in correct order or not. They are not in correct order. So we swap them. Here we will have 2 and here we will have 5. Again we update our iterator. Now it's pointing to this position. Now we have 5 and 10 Are they in correct order? Yes, they are. So after the second iteration, you have 3, 2, 5 and 10. You can clearly see. After the first iteration, the largest number went to the end of the array. After the second iteration, the second largest number went on the second last position. And that was our observation, right? After k iterations, largest k numbers will be at last k positions. I hope this is clear. Now let's go for the next iteration. So our I is pointing to number 3. Again we check whether 3 and 2 are in correct order or not. Here they are not in correct order. So what we do? We swap. So here we will have 2 and here we will have 3. Then our iterator will be updated and it will point to element 3. Again we check 3 and 5 in correct order or not. Yes, they are in correct order. So we update the iterator I and point it to 5. Again we check whether 5 and 10 are in correct order or not. So they are in correct order. So we will not swap. And in this way our third iteration is also over. And you have finally arrived at the entire sorted array. See? 2, 3, 5, 10. This is how this algorithm works. The key concept is our pointer is moving from left to right. And it will keep on swapping whenever order is wrong. So the largest number will be swapped every time, because if the largest number is somewhere in the middle of the array and not at the end of the array, then it will definitely create a wrong order. Look at the first iteration. This 10 is not in its correct position, so it will create a wrong order. So we'll end up swapping it. And we move this 10 to the end of the array. Same thing goes with 5 and same thing goes with 3 as well. And that's how this algorithm works. Now your task is to code this algorithm. This is just 3 or 4 line of code only. You should be able to code it. See, that's what we are trying to learn here. We are not just learning these algorithms to understand what bubble sort is. Nobody uses these algorithms anymore. Most optimized version of sort is available directly into the libraries in most of the programming languages. We are not here to learn bubble sort. What we are trying to do, we are trying to develop a skill, the skill of problem solving. To solve this problem, to solve any problem, you have a solution. To scale that solution, you automate it. That means you write a code for it. Or you find a way to convert your logic into the commands to the computer. I hope this is clear. And that's the skill that we are developing here. Try to convert this logic into the code. And that's how you start thinking in terms of the code. That's how you start thinking in terms of the commands to the machine. Okay, let's directly jump into the code. Here we are actually doing the logic. We are swapping if the jth element of array is greater than j plus 1th element of the array. That means these two elements are not in correct order and we are swapping it. This is the inner loop that we have that actually does the core logic. The outer loop that we discussed, we need to do this operation n-1 times. Why do we need to do this operation n-1 times? Well, it was very clear. After the first operation, we have the largest number at the end. After the second operation, we have the second largest number at second last position. So, after the third operation, we have third largest number at the third last position, right? So after the k iterations, you will have k largest numbers at the last k positions. So you need to do this operation n-1 times to get the sorted array. And that's what we are doing here. We are doing this main logic n-1 times, right? We check whether two numbers are in correct order or not. We swap them. This we do in one iteration and we get the largest number at the end. And once we do n-1 times the same operation, you get n-1 numbers at their correct position. And that's how bubble sort works. Next is insertion sort. Here the main operation is to select the number and you need to put that number in its right place. And that's the main operation here. This works because if we split the array into two different portions, let's say here it is the sorted array and here we have the unsorted array. So what we do, we select the first element from the unsorted array and put it into the sorted array at the correct position. So our length of sorted array will increase and length of unsorted array will decrease, and we will keep on doing this until our unsorted array becomes entirely 0. So what we are doing, we are selecting a number, we are taking that number and putting it into the correct position into the sorted array, and that's how we get the final sorted array. So we split the array into two different sections. Left one is always sorted while right one is unsorted. On this observation, we have this operation. Let's look at the example. This example will make it more clearer to you. So you have this array. First, let's split the array into two sections, left and right. So this is left and this is right. Left will always be sorted. So our iterator I will point to the very first element of the unsorted array. That means it will point to this 10. Our variable j will point to the last element of the sorted array, which is 3 here. Remember, our objective is to place this 10 into the sorted array at its correct position. So what we do? We check this particular 10 with the jth element. Currently it is 3. We check whether it is greater than 10 or less than 10. So if it's greater than 10, so we move this jth element forward and decrement the value of j. If this element, jth element, is less than the ith element, which is in this case 3 is less than 10. So we don't do anything because we know that this position is correct position for our ith element. So after the first iteration, you have something like this. This is our sorted array and this is our unsorted array. Again, remember, our pointer I will point to the first element of unsorted array and our pointer j will point to the last element of sorted array. Now what we do? We check the value of ith element and we check the value of jth element. Now here 10 is greater than 5. That means the position of 5 is incorrect. So we need to place this 5 at correct position. So if jth element is greater than ith element, we just move this value forward. So we are going to move this 10 forward and place it here. And we decrement the pointer j. Now j will be pointing to this value 3. Again we check our 3 with the element 5. See, this element 5 needs to be stored somewhere. Why? Because we are updating the value of ith element, right? Because we are pushing this element forward because 10 is greater than 5. So we will store it into a variable called as key. So we check the value of key with the jth element and we observe that 3 is actually less than 5. That means, remember, this left array is sorted array. All the elements to the left of 3 will be less than 3. So the correct position for the element 5 is going to be just after 3. That means 5 should go here. So we will place 5 here. So ultimately you have 3, 5, 10 and 2. So to write the formula clearly, you have a variable called key. We just saw the importance of it. You have the left array, which is completely sorted. You have the right array, which is unsorted. You have iterator I pointing to the very first element of unsorted array. Also you have a pointer j that is pointing to the last element of sorted array. So the value of key is going to be the ith element, the very first element of unsorted array, that is 2. So what we do? This is just an initialization process. This entirely is just an initialization process. So what we do? We check the value of key with the value of j, which is 10. Now 10 is greater than 2. If the value of jth element is greater than our key element, we move this element forward, right? So that's what we are going to do. We are going to move this element forward. Now we will update the value of j. Now j will be pointing to this element 5. Again, we check this 5 with our key element. Again, we observe that 5 is greater than our key element. So we need to move this 5 as well. So we will move this 5 here. After that, we update the value of j. Now j is pointing to element 3. Again, we check value of j with value of key. Value of j is greater than the value of key. So what you do? You again move this forward. Now, so j has reached the end of the array. So you need to put the value of key, that is 2, to the j plus 1 position. So ultimately you have the sorted array 2, 3, 5, 10. So the main thing here to understand that we are one by one selecting the elements and placing them into the already sorted array. And our base condition is that if we have one element, that will always be sorted. And that's how we started. Remember, we said that this is our sorted array and this is our unsorted array. So we took one element out of it, which is 10, and put it on the correct position. And that's how this algorithm works. Let's look at the code. So as I mentioned, this is the initialization part. We first update the key element, then we update the value of j. Remember, at the beginning, j is always I-1. Why? Because I was the first element of the right array, an unsorted array, and j was the very last element of sorted array. So j will always be I-1 at the start. So this is our initialization portion. You first initialize all the variable that you need. We update the value of j and move the value forward if our jth element is greater than the key element. Look at this inner loop. We decrement the value of j and move the jth element forward if and only if array of j is greater than the key element. That's what we are doing here, right? See, we moved this 10 to here. Why? Because 10 was greater than our key element. Again we moved this 5 here. Why? Because our element 5 was greater than the key element. Again we did the same thing with 3. We moved 3 from here to here. Why? Because 3 was greater compared to our key element. And that's what we have written here. If the jth element is greater than our key element, then we are updating it to j plus 1 position. That means we are moving it forward and we are reducing the j iterator. Once this entire loop is done, that means we have found array of j which is less than our key element. So j plus 1 position will be updated by the key. Now look at this outer loop. Remember, I is the first element of unsorted array. As we said, we start from the base case, assuming that one element will always be sorted. So that means our I will start from 1, it will go to 2, then it will go to 3, something like that. So I starts from 1 and it will go to n minus 1. So now you understand the outer loop and you also understand the inner loop. Okay, now let's discuss about selection sort. Key operation that we do here is that we select the smallest element from the unsorted portion and swap it with the very first element of the same unsorted portion. So let's say you have this array which is entirely unsorted. You select the smallest element and you place it on the first position. So what will happen? Now you have this sorted element and the entire unsorted array. Again, what you do? You select the smallest element and you put on the first place. Now you got two elements in correct position and you have this entire array. You select the element again and you put it on the first position. Remember, you are selecting the smallest elements, right? This is the smallest element from this entire unsorted list. This is again smallest element. The first position is deserved by the smallest element from this entire array. The second position is deserved by the smallest element of this array, right? So this is what the selection sort is. Let's look at the example, and selection sort is the easiest one. So let's say you have 3, 10, 5 and 2. So which element is the smallest element? Well, it's 2. So what you do? You place the 2 here and you place the 3 here. Remember, we are swapping the smallest element with the first element of unsorted array. So this was your unsorted array and you swap the element 2 with element 3. Now you have this sorted array and this as unsorted array. Again you select the smallest element, which is 3, and you place it here. So now you have this sorted array and you have this unsorted array. Again you select the smallest element, which is 5, and you place it here. Now you have entirely sorted array with you. Try to code this logic as this is very straightforward and easy to understand logic. What we are doing, we are finding the smallest element and then we are updating it with the first element. That's all we are doing here. Nothing crazy. Let's look at the code. So initially we have a variable called as minimum index. We assume that the smallest element is going to be ith element. We start our inner loop from the i+1 element, the very next element. We iterate the entire array starting from i+1 and we find the index with the smallest element, right? See, whenever array j is less than array of minimum index, then we update the minimum index. So we find the index of the smallest number. Then what we do? We put that element on the ith place. I is starting from 0. So when I is 0, we find the smallest number and we put it on the 0th position. When I is 1, we find the second smallest element and we put it on the first position. And that's how this algorithm is working. Now let's look at the time complexity. If you look at the code for all the three of them, see, this is bubble sort. So you have outer loop and you have inner loop. Outer loop is going till n, inner loop is also going till n. So you have n square. Same thing goes for insertion sort as well. You have outer loop which is going till n and you have inner loop which is starting from I-1 and going till 0. So that means this will also be n. So again you have n square here as well. See, what is time complexity? In normal terms, the time complexity is the number of operations that we do in a code and we try to represent it in terms of the input. So what is the input length that we have? That is n. So we are trying to represent the number of operations that we are going to do in this particular code in terms of n. That's what we are trying to represent. See, when I is 1, j will go from 1 to 0. That means 1. When I is 2, j will go from 2 to 0. Something like that. Again 3. Again 4. Till n. J will go from 1 to 0. When I is 1, j will go from 2 to 0. When I is 2, j will go from 3 to 0. When I is 3. And what j is doing? J is just updating the number, right? These are exactly two operations. This is the first operation that we have and this is the second operation that we have. So this loop is doing exactly two operations. So the total time complexity is going to be n into n plus 1 by 2, something like that. So we say it's n square. So we remove this n by 2. We don't consider it because for large n square is very huge compared to n by 2. So we don't care. Again, same thing with here as well. You have two different loops. The outer loop is going till n and inner loop where we actually have the operation where if you observe carefully, j is moving from I+1 till n. So for I is equal to 0, j will move from 1 to n, total operation n. For I is equal to 1, j will move from 2 to n, total operations are n minus 1. What do I mean by total operation? This. We are checking here which is one operation we are updating minimum index. The second operation. We are doing two operations here. We don't write that 2. We consider this as a whole operation. We don't worry about these constants and all. We are just trying to represent all the operations, no matter how many of them are, in terms of the input that we have. The input that we have is n, right? The array length. So we are trying to represent all the operation in terms of input that we have. We don't consider these two operations separately. We say okay, it's a constant operation and we will try to represent in terms of n. So if you observe carefully, it will be n plus n minus 1, similarly n minus 2 till you have 1. So it will be n plus n minus 1 plus n minus 2 till 1. It will be n into n plus 1 by 2. Again, n squared, right? We don't care about n by 2 because for large value of n square will be very huge compared to this n by 2. So we don't say time complexity is n into n plus n by 2. We don't say something like this. We remove all these constant numbers and we say the time complexity is n squared. So time complexity for all the three algorithms is n squared. I hope that is clear.